just a resume of the products of a coherent nuclear process. When the system reaches a very high coherent fraction, we have the products I described before. For a time less than 5 10 to minus 22 seconds, we have a gamma ray field that can eventually can rise photofission. And in the past, 2 years ago, we presented together to Professor Li a poster in Lerici in which he found a nickel element in our cathodes after the heat production. So it can be explained by this model. This theory is not model. For a time longer than this time, you can have soft X-rays and finally heat. If there is a low coherent fraction, I mean if you are just on the threshold x equal 1 of the starting of the process, you can eventually have that the hot nucleus breaks into part 3 plus 1, according to the scheme here, well known in the vacuum fusion, with the exception that in the matter, the two channels are not symmetrical with respect to the nuclear current. Because in this case, the nuclear current is obviously different than in this case. And the match between this channel here with the electromagnetic field is stronger. This is the reason why it's more easy to find tritium than neutron in this process. There's another class of phenomena that are soft X-rays found in a light water experiment that can be produced as a Bremsstrahlung due to electrons acceleration upon the deep plasma field. We have a situation in which we have almost free electrons in the lattice when you enter into the gamma phase. These electrons can suffer by acceleration due to electromagnetic field present in the matter, and they can be accelerated or decelerated and irradiate its energy. These are X-rays measured in light water. Now, for an experimental proof of what I said about the calorimetry and the difficulties in having calorimetries is what we found at the end of an experiment we did in Frascati. We found the cathode like this. As you can see, the cathode burned. It's not just burned, but it in some way blows up and deposits again on the cold substrate. In this case was aluminum. What we found is, I go fast. What we found is that not all the cathode breaks in this way, but just the last 3 lines that corresponds to the maximum voltage drop across the cathode. So, according to the preparata effect, to the maximum loading in the cathode. And we had a very high increase of temperature. We blow away palladium. This is another picture of the same effect. It's very evident. This is not Joule heating because the breaks happens not in only one spot, but in several spots along the last 3 lines of the cathode. But what we measured, the fusion temperature of palladium is 1800 K, and we expected from the Stefan Boltzmann law, assuming that only 5% of the cathode had suffered this effect, 1.2 watt. But our Peltier element measured just 20 milliwatts. This is the proof that this is not right calorimetry. We had to add more. It's not enough. So, conclusion. We found that the preparata effect is a very efficient and reproducible mechanism to obtain very high loading. We can gain from 30 to 40% more of loading using such kind of structures. And what is very important to stress is that if this effect is true, it implies the existence of coherent state in other matter. And this is, as far as I know, the only one known macroscopic coherent states in the matter. Using this peculiar loading, it's possible to have reproducible excess heat and to test several things. And what is important is also important is the helium-4 measurement is not only a proof of the nuclear effect, of the nuclear nature of this phenomena, but it's also the more reliable calorimetry we can do to explain the heat we see. Then what we have to do is to complete our calorimetry and eventually isoparabolic calorimetry and helium-4 measurement. So we have to design new different cells. Thank you.
Professor Takahashi.
Takahashi from Japan. I like your idea of coherence, but I think the nuclear reaction time of the deuteriums, even in coherence, cannot be so short as 10 to the minus 22 seconds. Because even at MeV, the reaction times are as short as 10 to the minus 22. So far, if the deuterium energy becomes very low, we need a longer time for nuclear reaction. And even if we are allowed to say the reaction time is as short as 10, much shorter than 10 to the minus 20 seconds, still we have problem that the breakup to neutron or triton emission channel, that the lifetime is estimated to be 10 to the minus 22 seconds also. And also the branching ratio is given as a ratio of energy width. That is the inverse of lifetime. So far, to explain the experimental result, heat helium without neutron, we have to explain the branching ratio between helium production and neutron production should be less than 10 to the minus 12 or so. So far, you have to require the lifetime, say, very short, 10 to the minus 30, 33, 34. That is very, very hard to clear.
It depends on the fraction of coherent, of the coherent fraction of the system. If the coherent fraction is very high, the probability to have breaks of EV.
Yes, to make a reaction, we need a time. Okay?
Yes. In time shorter than 10 to minus 22 seconds, it's very small.
So,
but it is
I mean, we need something like 10 to the minus 30 or more.
Yeah.
More,
the
much less.
Other channel, the channel that produces tritium and neutrons, is possible only if you have a not complete coherent fraction in the system. If you are just borderline on the threshold, it depends on the states of the lattice. Not on time.
The idea is heat is not, for me, that looks impossible.
Professor John Miley.
You said the field-assisted loading added 30%. What loading ratios do you get at which, and what do you need to get the excess heat you're reporting? And I guess sort of an auxiliary thing is you said if you have less than full coherence, you can go to the tritium channel. It seems like you're passing through that. Have you found any tritium?
It's not easy to say exactly which is the loading ratio because the Baranowski curve is available up to 1, more or less. It corresponds to 1.4 on the curve. We measured ratios less than 1. I do not know exactly what does it mean. Because you have to deload in galvanostatic deloading sample. Otherwise, how can be measured? But we know that we are under 1.4, that means over 1, x equal 1. We are in a cold region, hot region.
Dr. Celani.
Okay. Again, about the value of Bernoulli curve, if I am not wrong, even when you deload the palladium film, you never reach 2. Maximum 1.9, 1.8. Usually, after the loading, if you have a very large loading, you have a lot of stress accumulated in the wire, and the maximum overcome always 2. This is the proof that you have get large loading.
We produced a table that will be shown in the poster this afternoon, in which we report the maximum height for several load and deload cycles. And you can see that the deload maximum is always higher than the load maximum. But the dynamics of the sample tends to shrink from one load to another. I think that is because you cannot be sure that you deload completely after the experiment your samples, because we do not invert the current, electrolytic current. So if you don't evaluate correctly the R0 values, you can have a big error on the evaluation of the peak.
Okay, any more? Okay, Dr. Hoffman.
You expressed the excess heat in terms of the joules per second out being greater than the joules per second in, that is watts out versus watts in. What was the excess heat in just joules out versus joules you put in? You know?
I do not know exactly now. It depends on the lasting of the experiment. But typically one experiment lasts 2 or 3 hours.
But
So it's 20 milliwatts per 3 hours. You can hundreds of joules. The 100 measured by the Peltier element, of course.
Okay, let's sing again. Our next speaker is Professor Emilio Giudici.
I use the conventional.
Okay. While they are preparing, I just want to say, if you have any equipment like a computer, we may try before your turn. Ask this Mr. Zhang. He will test your computer in advance, then we will save time. Only.
Can you hear me? Yeah. So, while it's preparing the equipment, I would say that my talk will be an attempt of interpretation of what we know about the mechanism of loading high amount of hydrogen or deuterium into a palladium or in general a metal matrix. And this topic actually has to do with some delicate properties of quantum system, and it could be considered also beyond the problem of cold fusion as just a research on the foundation of quantum theory, because it exhibits typical quantum phenomena which have no classical analog at all. So they are very interesting also outside the frame of cold fusion. Now, this interpretation required the cooperation of many people that are listed over there. And by the way, I must say that Martin Fleischmann taught us a very important a lesson, namely that scientific archaeology is a very important piece of research. And it was true since we found a very interesting paper of two poles in the 1970s. And this paper, which is an experimental paper, is about the whole effect on palladium hydride system, and is meant to measure the number of carriers of the current as a function of the loading stoichiometric factor X. And a very important result comes out. So we must have a little bit of patience before seeing this Polish miracle. By the way, I began. Maybe. No, usually maybe. No. We need someone who has the military duty as an artilleryman. Anyway, let's start. You know very well that palladium hydride exhibit, apart from the alpha phase, at least two interesting phases, the beta phase and the alpha phase. At room temperature, the beta phase is up to a stoichiometric ratio X equal 0.7 about, and in the beta phase, hydrogens in ion form are located at a definite position. They can move, they can do very narrow movement, and the loading in this phase is an exothermic loading. Beta phase is quite different. Beyond beta phase, there is a strange new situation. I will show you now the Polish stuff. This Okay, you can see in this graph is represented as a function of x the number of carrier of the current as measured by the Hall effect. And you can see that there is just a discontinuity point at about x equal 0.8. Since in the paper is not defined what was the temperature of the experiment, maybe this 0.8 will be just the beta gamma transition. I don't know, because we are used to consider 0.7, the transition point. Here is point 8. But the paper, which is a short letter, actually is not very clear about. In any case, there is a discontinuity point where the slope of this behavior changes abruptly. But if we discuss what that means, we got an astonishing result. Namely, let's consider the first part of the graph. In this first part, which corresponds to the beta phase, each new hydrogen entering into the lattice contributes 0.7 electrons, more or less, to the conduction band. The other 0.3 are given to the low-lying deep band and contribute to a change in the magnetic susceptibility, which is actually observed. So everything is regular, everything is accounted for. But the very strange thing occurs when X crosses 0.8, because in this new situation, every new hydrogen entering the lattice contributes 6 electrons to the conduction band. But you can say, but we know very well, after Bohr, that hydrogen has only 1 electron. So, apart the miracle of the multiplication of electrons, we can interpret this result as saying that each hydrogen entering into the lattice contributes to the conduction band its own electron, and moreover persuades, let's say, 5 electrons of the palladium to shift to the conduction band. So the entering of the hydrogen induces a reshuffling into the structure of the palladium-hydrogen system and induces a phase transition. Which kind of phase transition? According to the ideas that Giuliano Preparata told in the previous conference, we can interpret the localization of hydrogens in the beta phase as induced by the potential well produced by the electrons, the d electrons of palladium, which through their collective motion produce point in the lattice where there are deep potential well. Now, in this new situation, a portion, a fraction of these Warden electrons is promoted to the conduction band. And this produces 2 main consequences. First of all, explain the falling down of the resistivity curve. Because there are more carriers, of course, the numbers of carriers multiplies, so the resistivity decreases sharply. And the mystery of the bell-shaped curve can be accounted for, first. Second, by this multiplication of carriers. Second, there are less electrons to confine the hydrogen in the lattice, so instead of deep and narrow potential well, we have, as Martin Fleischmann predicted a long time ago in the 70s, I guess, that hydrogens are able to oscillate within wide and shallow potential wells. So the 2 phases are characterized by beta phase, deep and narrow well. Gamma phase, wide and shallow well. Within this shallow well, hydrogens are able to perform wide oscillations, and according to the theory of coherent plasmas of Giuliano Preparata, it's possible to check that the frequency of this oscillation matches the coherence condition. That means that these nuclei are able to oscillate in unison and produce a coherent state. Which are the energetic consequences of that? First of all, the loading becomes from exothermic, as was in the beta phase, endothermic, since we need the energy to raise 5 palladium electrons from the deep band up to the conduction band. But the chemical potential, on the contrary, decreases, since once this miracle has occurred, now the chemical potential of the coherent plasma of hydrogen is lower than the chemical potential of non-coherent hydrogens. And this state is provided that is produced, provided one has paid at the beginning the energy price to load, becomes a stable, coherent state. Further consequence of this. So, now, but maybe it's better that since the precarious nature of the projection, I will project only the graphs to you, and the talking I will do. So, next problem. If an ensemble of particles is described by a unique wave function, what is the consequence? Because in the beta phase, we have a mixture of wave functions, because each hydrogen has its own wave function, and the ensemble is described by a statistical matrix, a density matrix, so that there is no definite phase, because each particle has its own phase. But when coherence starts, means that there is a definite phase for every body. So every one oscillating phase, there is a unique wave function which describes everything. Consequence, as in the 50s, Böhm and Aronoff showed, when this is the case, since Schrödinger equations tell us that the potential appears in the phase, if the phase is undefined, you cannot discover any potential. So you can discover only the fields. But if there is a measurable phase, at that point you can discover also the potential. So a quantum system is able to detect a potential contrary to a classical system. What that means? That since the potential appears in the phase, and the chemical potential too is defined by the phase, that every externally applied potential adds up to the chemical potential. So you have that the chemical potential, when there is an electric potential V, is equal to the chemical potential without the electric potential plus the charge times the potential. So if you are smart enough to apply a negative potential, you can decrease the chemical potential and you can lower the barrier that prevents the entering within the lattice. So in the gamma phase, the loading is made difficult by the existence of a high chemical potential. You apply to the cathode a negative electric potential, and the barrier decreases. So this is a different approach than the usual one. Usually, when there is a difficulty, one tries to eliminate the difficulty by using brute force, by violence. This is a different approach because we try to gain the entrance into the lattice by seduction, just by lowering the barrier instead of increasing the kinetic energy. And of course, you can make to me a devastating objection. You can say, yes, but if you apply a potential to a cathode, you get the current according to Mr. Ohm. And if you get the current according to Mr. Joule, you get heat. And according also to Mr. Preparata, heat destroys coherence. So, at last, you could have a zero-sum result. But we can overcome these difficulties by having a very high resistance, because, of course, a potential transforms itself into a current modulo a resistance. If we take a resistance high enough, we get a very small current and very small Joule effect. How we can do? and we are forced to use one-dimensional cathode. If we use a massive, a bulk cathode or a plate, of course the resistance is quite low and the variation of potential across the cathode is tiny. But if we use a wire or a stripe, like Antonella before has shown to you, namely a long cathode, that is 1 meter, with a very tiny cross-section, a width of 50 microns and a thickness of 2 microns, this produces a resistance high enough that also if we apply 10 volts, the field is 0.1 volt per centimeter, and the Joule effect is negligible. So in this case, we can get the good result of having the attraction without having the bad result of destroying the coherence. So what happens is, if we apply the potential before reaching the top of the beta phase, we get nothing, because there is no definite phase. When the system reaches a loading of at least of 0.7, suddenly, at that point, the applied potential induces a dramatic fall of R over R naught, which is the proof that there has been a large increase of X. And I will show you now the graph as promised. Okay, and you can see, in the lower graph there is the application of the potential, and simultaneously with that R over R naught was stable because we had reached the peak of the beta phase, comes down. That means that there was a barrier of chemical potential which prevented the entrance. Apply the potential, the barrier comes down, and there is an inflow of hydrogens. Consider that this phenomenon, which is a quantum phenomenon, has nothing to do with electromigration, which is a totally different thing. Because electromigration means that you push the hydrogens along the wire and produce empty space for new coming hydrogen. In this case, you apply a potential along the wire. This produces a lowering of the barrier, and an inflow of hydrogens enter from the sides. So a longitudinal field produces a transverse effect. This is very important. And unfortunately, I lack here a third graph who was there in the previous situation and after it was lost, that shows a startling thing, that the excess heat appears just shortly after this transition. And the time of delay is less than the time of response of the calorimeter. So it could be considered simultaneous in this effect. So let's summarize. Apply the potential. R over R naught falls down. That is the proof that X is coming up. You overcome the threshold, and the excess heat starts. And the era of nuclear physics has started. And this is the preparatory effect, which is the essential tool for achieving the loading high enough to have the nuclear phenomena. Just now, one last chapter, and after I will leave. How the bulk of the people were able to load this system without using this effect, but loading for a long time, days, weeks, months, and reaching at last the threshold. The problem is that it can be shown that on the surface, electrolyte electrode appears in the gamma phase a capacity, an electric capacity, which is absent in the beta phase. Why is absent? Because hydrogens arrive to the electrodes, they find their way open since energetically the electrode is a well, is a pit for them, so they follow, and no accumulation of charge occur on the boundary. But when we reach the saturation, at least the temporary saturation of palladium, hydrogens cannot enter any longer. So they choose the long way of the gas evolution. That means that they crowd just on the surface of palladium, and they are able to charge the capacity which is there. Which is the origin of this capacity? This should be found, as Martin Fleischmann told before, in the new theory of water we produced. That means something like that. In the coherent region, water molecules are in a peculiar state because the coherence is such that there is in each molecule an electron which oscillate between the ground state, where is tightly bound, so water in this state is an insulator, and an excited state which is just below the threshold of ionization. So in this new state, the water is almost a conductor, the coherent part of water, not the whole water. And for each molecule, there are 0.13 electrons at each moment in this state. So the surface of the coherence domain acts as an armor, a metal armor of a capacity. Nearby the electrode, there are the surface coherence domain, and below there is the surface of the electrodes. The interstice between the two is just the frontier region where coherence disappears and non-coherence appears, where molecules lose their tune with the coherent oscillation. And the depth of this region depends on temperature. So the value of this capacity depends on temperature. At room temperature, this region is deep 40 angstrom, and the corresponding capacity can be estimated from this number as 20 microfarad per square centimeter, which is quite okay. We have a graph which shows the falling down of the cell voltage when switching off the current. That ensures, by the way, that we can stop for very short time the current of the cell for measuring the resistance without losing anything, because you can see that there is a discharge curve whose typical time is more than 1 second, 1.16 seconds, which correspond, given the cell resistance, to a capacity of about 20 microfarad per square centimeter of the electron. So we have the theoretical prediction and the experimental check of this one. Now, last argument. Given the appearance of this capacity, in the gamma phase, we should expect that this capacity, which is uncharged in the beta phase, becomes charged. So we should expect that the potential, the difference of potential between the cathode and the reference electrode put nearby the cathode should show an increase corresponding to the charging of this capacity. And that's actually occurred. Not only, but when this capacity is very well charged, we should expect instability. We could produce instability by giving AC modulation. But since current is not always perfectly steady, we should expect the spontaneous appearance of oscillations. And each oscillation is a push for ions within the cathode, because a capacitor which is thick 40 angstrom and which has a potential of about 1 volt between the two, induces an accelerating field very high. You can understand 1 volt divided 40 angstrom is quite a big field. So there is no chemical potential barrier who could prevent the entrance to such hooligans. And they arrive in full strength. Of course, you need many discharges like that to load, but if you are patient enough, you can reach the load. Of course, you should increase the instability of the current. Maybe the use of ramps, as usual, since the content of a ramp is the full spectrum of frequency. You don't know what is the resonance frequency, but in a ramp, certainly there is also the resonance frequency. And in this way, what we need. Now, I end my talk with the firecrackers. I will show you. First of all, there is, forgive me, but I am a theoretical physicist, so not particularly able to manage this experimental stuff. You can see a perfectly steady cell current and cell voltage. And you can see what is the fluctuation of the voltage, the cathode reference voltage at last. You can see that there is a magnification. No. Okay. You can see that these oscillations are quite regular, are not random at all. There is a typical period of 22 seconds. And this is totally spontaneous. So they are switched on just by the spontaneous irregularities, small irregularity of the current that induce this oscillation. And this oscillation pushes violently. The preparate effect was seduction. This is violence at high speed. And you can see what are the consequences. Since our cathodes are very thin, the microphotography of what happened to the cathode and to the substrate of the cathode because of this bombardment of accelerated ion. I have two impressive graphs. First one. Unfortunately, there is. It's possible to improve. No, I need to improve this one. In the picture at left down, it's very difficult to. Yes, here. In this, Professor Lee, I'm a theoretical physicist. I'm totally unable. Okay. You can divine and not see just that here there is just a sinusoid. This sinusoid, which is very regular and lasts very long. What is it? Correspond to an excavation in the substrate, in the silica substrate of our cathode, deep 4 microns, and wide almost the same. And the typical thing is that the radius, the radius of this oscillation, I'm almost unable to see now. I don't know. But anyway, who is interested can see just can see the picture. The radius of these waves are some tens of microns. And which is this figure? Is exactly the size of the coherence domain expected in a crystal structure. So that would be the first time that we have a micrograph of the coherence domain. Because why these lines are not straight lines, but are just wave lines which last very long, I say. So that hints to a regularity. And in the other figure, this is a magnification, of course, here. And in this valley, which resembles the Grand Canyon of Arizona, there are pinnacles and towers that you can see, which are like the funnels through which the material evaporates. And all this disaster, who is the author, the culprit of this disaster? Since this experiment was done with light water, this process is nuclear looking, but is not nuclear, this particular process. Is just the devastation produced by the ions coming at high speed, accelerated just by a field which is 1 divided 4 minus a field which is 2.5 times 10 to the 6 volt per centimeter. They arrive accelerated at this speed and they excavate, producing in a way X-rays. And I know that Dr. Violante will present here an experimental paper where he shows that electrolysis with light water, not deuterated water, induce the presence of a given amount of X-rays. And the presence of X-rays is consistent with just the stop of these ions arriving on this material and stopping there. Okay, I believe that I've finished.
Thank you very much, Professor Giudici. We have to go to your post session for the questions. Right now, we give the time for a coffee break. But please come back very quick, because this is important. The coffee break is a little bit unimportant. Please come back. Go to coffee break first. Okay, 10 minutes later. 10 minutes later, come back.
Thank you, Mr. Chairman. I think you will know my English is very bad. All of you maybe understand difficult. So, Professor Lee recommended me to send 3 papers in here. Please read it. The first, right? This is our proposal. Nuclear fusion generated in Lux reactor or metallic deuterium Lux using metal atom cluster. And after, so, formation of highly condensed metallic deuterium Lux and nuclear fusion. And second, nuclear fusion caused by intentional implanted death, and some other. The first, at present, in order to approach nuclear fusion 2 ways, using gases in left side, and another metals in right state, right side, but ultra high temperature gases method, it is not so easy. Long time necessary. On left side, the reaction, 15 years ago, we developed the first in Japan. But even at the present, still not so good progress. But metal side already is realized many stars in universe under metallic hydrogen with ultra high pressure 10 to 11 to 10 to 12 atmosphere. It is well known in astrophysics that this is a technonuclear reaction. Techno means ultra high density increase. Also, at the present, there is concept of artificial technonuclear reaction on the Earth using metallic hydrogen under 10 to 9 atmosphere. But this is still a dream project due to extremely difficult technological viewpoint. So that how we can approach the necessary condition for technonuclear reaction, we have used deuterium lamp by using metal atom clusters, showing at the right column. These metal atom clusters show such anomalous behavior as spontaneous mixing of guest atoms. That is, deuterium atoms are instantly absorbed into palladium atom clusters more than 300% in atomic range against palladium. And these atoms coagulated locally in cell of host lattice as deuterium lamp. In this case, deuterium density corresponds to about 10 gram per cc under ultra high pressure of several 10 to 8 atmosphere. Thus, such deuterium lamps cause technonuclear fusion inside the unit cell of host lattice, which plays a lattice reactor. Here, it should be emphasized that these deuterium are not necessary to move about within metals for nuclear fusion. Next slide. This shows a typical example of spontaneous mixing of guest atoms into host atom clusters. Upper series show formation process of an atom cluster. Left side, liquid phase, center zone, maximum size atom cluster, and right side bulk solid, and second series, relation between bonding energy and surface energy of the atom clusters. When host and guest atoms are gold and copper, respectively, vapor deposited copper atoms are instantly absorbed into gold clusters. This is because host atoms within gold clusters can easily displace about 10% of neighboring in the atom distance. Did you understand? Maybe. As a result, diffusion velocity of copper into gold clusters is more than 10 to 9 times against bulk gold crystals. And moreover, atomic range of copper versus gold, because up to more than 300%. Slide, please. This same spontaneous mixing of gas deuterium more quickly occurs. This slide shows concentration of the atoms is 300% against host palladium atoms, and these correspond to mixing of 200, 300, and 400 in unit cell in host metal clusters. This event is demonstrated in detail later. These remarkable difference between atom clusters and bulk metal decide whether nuclear reaction succeed or not in atom clusters. This is just a very important situation, but only trouble of atom clusters is easily sintering during experiments. Next, please. In order to avoid this trouble, we have developed special type paradigm cluster, which embedded within ZRO2 powders, as shown in this slide. First, amorphous ZR65 paradigm 35 was prepared and heated in air so that the zirconium was oxidized. As a result, paradigm clusters of amount about 50 angstrom were embedded within ZRO2 matrix. Middle zone electron micrograph shows paradigm clusters. Next slide. Paradigm no. Okay. This is more detailed microphotographs of 50 angstrom paradigm cluster. We surprised to such beautiful distributed clusters. As you see, paradigm clusters are exactly isolated. Just this is a very important event. In left side figure A, the first sample was kept 2 days under high vacuum 10⁻⁷ torr inside the stem field vessel, which was immersed in cooling water. After that, B2 or X gas was injected into the vessel with constant gas flow of VG equal 20 cc per minute. In this case, necessary parameter is chronologically changed in a pressure and both cooling water and sample temperature. In right side, where we absorbed quantity of B2 or X gas can be indicated by atomic ratio and chronologically changed sample weight. And these both results were indicated with almost the same sample weight, chronologically changed sample weight, and these both results were indicated with almost same. Using figure A method, as shown just before slide, diagrams A, B, C were obtained, and using figure B method, the diagram was obtained, and the red colored point of A, B, C shown in each diagram correspond to same inner pressure, respectively. For example, point A in diagram A shows measuring elapsed time, minutes at 0.1 atmosphere inner pressure, and in diagram B correspond to absorbed gas volume during minutes, and in diagram D show atomic ratio, and also point B, C show same way. Using diagram A and B, atomic ratio of absorbed gases can be introduced as shown in bottom side. And diagram C shows that ZRO2 matrix did not absorb at all. Consequently, diagram A, B, C, and D demonstrated that palladium atom clusters can be condensed much deuterium. For instance, even under 0.1 atom, absorbed the atom density exceed considerably to 100%, and at 3 atom exceeded to 255%. And also measured 100 atom succeed 300%. This slide, next slide please. This shows formation of heavily condensed metallic deuterium gas. As you see, right side top corner diagram B. There are two kinds of gaps shown with open circles within a unit cell of FCC structure. That is octahedral and tetrahedral site. Therefore, when all sides of these gaps are occupied with D or H atoms, its atomic ratio becomes 300%, as shown right side of third line. That is small a in parentheses inside large F. Unfortunately, however, T side gap is too small for D or H atoms. So only O side has large space receiving enough D atoms. And thus, as shown just before slide, even under condition of about 1 atmosphere inner pressure, much D atoms with 200 to 250% embedded continuously into atom cluster without any resistance at all. This event definitively designated existence of 2 or 3 D atoms inside O side space. That is, O side space is called simply octavessel. In other words, 200% rats and 300% rats are formed, and mixed condition of these rats were realized. And also in case of atom cluster, absolute 300% the atoms as shown just before slide correspond to form 200, 300, and 400 rats. In other words, octavess including from 2 to 4 the atoms exist in the atom cluster. Under such high inner pressure and several hundred to 1,000 atmosphere, it is considered that atoms are almost octavessel includes 4 the atoms coagulated with tetrahedral structure, simply called deuterium ring, which are shown in photograph, centered in top side. Such highly condensed host shown in photograph, centered in top side. Such highly condensed host atom cluster are constructed with metallic deuterium rats as shown in figure 3H. Next slide. Next slide. Now, when following condition is realized that only 1 T atom can steadily stay inside the tetra vessel, octavessel can easily include 8 D atoms, as shown in this slide. That is, when yellow ball designate the atom added in deuterium ring, yellow ball increases from 500% up to 800%, and red colored tetra ball join in octaball from 900% for the first time. Consequently, Although red ball can pass instantly through a tetra vessel, 4-octa vessel, cannot stay steady there due to too strong atomic bonding energy, especially in bulk metals. As a result, doors of tetra vessel in atomic cluster are considerably loosely constructed, but which is very hard in bulk metal. And one tetra vessel controls function of 4-octa vessel, as shown in bottom side lattice of this slide. Next, please. No. Here, it is very important to note that constituent of the atoms in technodeuterium RAM consisting of tetrahedral 4 the atoms coagulated intensively each other, and thus any diffusion among the atoms does not necessary at all to approach each other. Under such condition, nuclear fusion results in last reactor by some physical shock, such as a earthquake. And as you know, we have shown many times through many experiments up to date, but in bulk metal, it is necessitated following 3 stages to realize nuclear fusion. This is a fact. They must be moving beyond steep barrier tetra vessel, because the atoms in octa vessel are always separated by tetra steep barrier each other. Because the atoms, so that is the first. They must be moving beyond steep barrier tetra vessel. Second stage, they must approach each other. Third stage, the atom must contact each other, and moreover, they should be coagulated. After that, it should be checked that how many groups of such coagulated the atoms generating bulk metal specimens. And when we consider on above 3 stages in deuterated bulk metals, which essentially go concentration, just as impossible exceeding host metal density, generally cannot be imaginated, causing nuclear fusion inside bulk metal. If you still consider that nuclear fusion can also occur even in bulk metal specimens, you have to clarify why atomic ratio of decreasing against metal atoms cannot exceed 100% within such bulk metal specimens. Although we are understanding metal atomic bonding is very strong, and besides, diffusion of deuteriums will be rapidly decreasing with increasing of concentration inside solid bulk metals. And therefore, the atoms under maximum concentrated condition will be apparently isolated and stopped. Thus, limited concentration will be realized inside the bulk metal, which does not succeed 100% at all. These, okay, next please. Finally, in this section, this shows relation between excess energy and helium generated inside open-type DS cathode. We have reported similar data up to now, many times every year. Left side excess energy and right side helium generated inside open-type DS cathode. To measure continuous change of inner pressure inside cathode DS cathode. And cold shortly DS excess energy and DS helium respectively. A shows left side DS excess energy, in B shows right side DS helium using VI effect. Note, in left side diagram, A current stop B inner gas test. Inner gas B added to 20 cc and added to 10 cc regular 20 cc and CP zone, controlling zone to get constant excess power. Okay. And next. Next item, solar implantation effect on nuclear fusion. These listed papers here already have been published. We named solar implantation as technical term and clarified intense solar implantation effect in detail, so that present report is one of the application of solar implantation effect and clarified on whether intense solar implantation effect causes solid state nuclear fusion or not. Next. This is a solar implantation system. A is solar vessel, B is solar violator. The first sample kept in bottom of working space inside solar vessel. After that, working space was vacuum at 10 to minus 2 to 10 to minus 3 torr. And the second, the last working liquid was supplied there. After that, working gas was immediately introduced there to keep to atmospheric pressure. Solar vessel was cooled by cooling water through chiller system, and solar output can be obtained by temperature difference of both sides of the chiller system. Sonic power of 300 watts with 19 kilohertz during about 1 to 2 days was supplied to metal coils immersed inside working liquid. As a result, metal hoist changed into the ultrafine powder of nanoscale, nanometer scale, which are called simply some powder. Lower side, electron micrograph shows gold sono powders as a typical example of sono powders, because gold has been considered to be very stable metal for chemical attack, but color changed into black because of their size of 50 to 100 angstrom nanoscale. This slide demonstrates the intense sono implantation effect on the working gas of inert gases such as helium-3, helium-4, neon, argon, xenon, which were strongly implanted into sono powders. Implanted inert gases can be released into quadrupole mass spectrometer called simply QMS when heating sono powders. Upper side diagrams demonstrate chronological change QMS intensity of inert gases released from heated sono powders. Left side diagrams A and B show strongly implanted helium-3 and helium-4, respectively, which were released from inside the paradigm sono powder treated by HO working liquid. Right side diagram C and D show also strongly implanted neon and argon, respectively, which also released from paradigm sono powders treated by D2O and HO working liquid, respectively. Here, it is well known that neon and argon gas, as you know, naturally mixed as neon 20 and neon 22 and argon 40 and argon 36 with constant ratio, respectively. Although we use commercially pure neon and argon gas as the working gas, as you see, the C and D diagram, these inert gases are beautifully and strongly implanted with naturally laid. Lower side diagram shows anomalous difference between working gases such as inert gases and nitrogen gas against non-working gas. This event demonstrates definitively important characteristics to cause solid-state nuclear fusion, simply solid fusion. This slide demonstrates intense sono implantation on the working liquids or only D2O and HO liquid without working gases. That is the atom or H atom dissociated from D2O or HO liquid are strongly implanted into many metals, and their sono powders were formed. And diagrams A to E in the upper series show relevant mass intensities of first group of mass M2, M3, and M4 within paradigm virgin, paradigm HO, paradigm D2O, and others, titanium D2O, silver D2O. And moreover, corresponding diagrams in the lower side series show those of the second group masses M18, M19, M20, and M22 within the same metals mentioned above and respectively. By using spectrum intensities in these diagrams, anomalous intensity difference between T and H atoms implanted into sono powders can be determined as following equation. Finally, it is concluded that the implantation effect on the atoms more than 1,000 times larger against H atoms. This is the implantation effect. It is extremely strong compared with H implantation. This event is just definitively important to code solid fusion. Using high resolution of type of QMS, spectrum of helium-4 and helium-3 can be detected as shown in upper series. But when M3 hydrides increase higher level than helium-3, say helium-3, which can not be detected by QMS as shown in second series. So we have developed VI effect to detect helium-3 as shown in lower side A and B diagrams. Left side A diagram is similar amount of M2, M3, and M4. Right side B shows M2 amount of 100 times larger than M3 and M4. Here, helium-3, helium-4, and hydrogen were discharged from pure gas tanks, respectively. To obtain this diagram, intensity current per 2 voltage at given applied voltage, which is changed automatically from 17 volt to 40 volt, are detected automatically. This event called simply VI effect. Using this method, helium-3 can easily be detected even if helium-3 is a little. Bottom side diagrams in A and B diagram called normalized VI effect. Next. This is VIF effect on sono powders of palladium, titanium, gold, and silver, with these working liquid as shown in middle and right side column. Helium-3 and helium-4 are accurately discriminated from DH plus H3 and D2 plus DH2 respectively. And although these heliums generated within some powders of these all metals in the palladium and titanium sono powders were obtained considerably larger than gold and silver sono powders. Please, next. This shows one example of another spectrum of mass M4 and M3 released from sono powders. Upper side series show QMS spectrum of mass M4 released from palladium virgin, palladium XO, and palladium D2O, as you see. Palladium virgin spectrums show very little amount of D2. Palladium XO show no helium-4 and much D2 amount. Palladium D2O show accurately helium-4 and extremely large amount of D2. Bottom side spectrum show clearly existence of helium-3, TH and H3 within silver sono powders of silver ditto. Okay. Hold. This slide shows sono excess energy generated during formation of sono powders, in which D and H atoms were strongly implanted into palladium, titanium, and gold using DSO and HO working liquids respectively. Upper side show chronologically changed sono generate output power in palladium, titanium, gold sono powders within DSO and HO working liquid respectively. Lower side series show chronologically changed sono current respectively. Consequently, sono excess energy are obtained under both side equation. Oh, okay. And another item. I would like to talk the last topic very briefly. As I mentioned, already solid fusion result from that reactor within metallic deuterium lattice by two methods of DS cathode and sono implantation effect. Some perform. This next. So here we can expect that host metal atoms surrounding that reactor are also strongly affected by this solid fusion. Our group has already obtained some results showing this phenomena. This slide shows sample folder and next. This is the base of tritium amount between virgin after. After treated, liquid left side after virgin. Almost nothing. And the right side also metal after virgin. Working liquid included the such metals. And it's all mixed from some deuterated metal almost nothing. Ratio, okay. This is apparatus or vision and red color is sample. Next. So DSA, DST, DSA, DSO, DST, XO. This is series current, series electric current using. And so you can see D2O, DSA palladium 102, not so much, not so, but iridium 121 and gold 127, about 8 times or 6 times larger than H2O. This is gamma ray. Oh, this is possible explanation of this amount. Yeah. And, this is our concept as conclusion. In detailed experimental data, this soon published High Temperature Society in Japan, also the same society. Okay, thank you.
The paper is open for discussions. Other questions? Yes, Professor Maidi?
The measurement of the radium 119 and the gold 197 is very interesting and important. What was the detection level for the other? You had raised a question if you why you only saw those two. What detection level would you have for other isotopes? You were using. How do you know there were not more elements than the two?
He said he made a neutral activation analysis and found these two elements by activation using neutron. He used the reactor neutrons to make the activation analysis. But he didn't know why they found only two.
But the sensitivity for some other elements is not that high with NAA, so it may be that other techniques will disclose additional elements.
He said that he didn't find any others. He used JMPR material irradiation test reactor in Japan for NRA analysis and reduce fluxes. But maybe, in my opinion, the sensitivity for other elements must be high, also high. That means he did find only two elements. Okay?
Thank you for the answer. Further question? Yes, Dr. Basil?
Dr. Rana, these reactions you have shown, I don't see them as having a positive cue for always assumed we had to have a positive Q in order for these reactions to occur that you've shown. I wonder if you've calculated the Qs for these reactions to see if they are indeed positive or not.
He said he didn't check that. He didn't check that, whether the Q1 is positive or not.
Yeah, I think it's the answer not given in the first sentence, compound nuclei.
Well, he assumes the two proton will make a fusion and then split into two, like a fission. So which have enough fission energy to make this, split. Okay.
So thank you. Other questions? If I may then ask a question from the chair, please. At the beginning, you were talking about these nuclear deuterium lamps with about 50 times higher density than deuterium gas, deuterium solid. So 50 times higher density would mean that the electrons have to be squeezed to a Fermi energy of about 5,000 eV. Is this reasonable without any plasma? Yeah, thank you.
Correspond to 10 to 8 atmosphere, such a condensed. Yeah, and this is a very important point on all sides. And many electrons, post-metal electrons, cancel space charge. This is very important point. So, theoretically, from now, theoretically, electromagnetic, very important. How to distribute inside of the hadron, not yet in detail. Just now, from now, very newest physical mechanism.
Thank you. If any further question? If not, then we have a few announcements here from the organization. And I would like to repeat, after the lunch, the session begins again on time at 1:30. And please note, after 3:05, there's a 25 minutes talk of Dr. Basti.
Okay, attention please, ladies and gentlemen, and may I announce something before you reach the level of your stomach? And first I'd like to know, since we're going to the Great Wall on Wednesday morning, so after that we're going to see some experiments, and the wives and families can go some little bit tour after that. So for everything better, we'd like to know is if anybody canceled your trip on that day, just let me know around lunchtime. Okay, I'm easy to tell, just let me know the number exactly, because we have to arrange in big bars and the sandwich and waters. So thank you for understanding. And second of all, I like to say it is a time for our group photographer. So we'll have boys and girls and bring over. You get out from this exit on the right side. So just to follow all the people. So we'll have that photograph on the third floor. And lately, I think think that's all for now. I may have something else to tell you. So thank you for listening to me and enjoy your dinner. Sorry.
Here the presentation by Dr. Bassel.
Oh, wait, just wait a little bit.
We have no time. Go ahead.
Ah, you saw my seat.
Oh, were you here?
Yeah.
I'm going to move.
Okay.
Didn't know if anyone was here. I wanted to get a better angle for the... I can't steal your seat, you know that. Excuse me.
I am now the chairman.
You should have some blow up.
Dance, yeah. Well, I agree in general as the chairman to start on time when you say you're going to start on time, but you know how that goes. When I've been chairman, I've usually given them a 10-minute warning, a 9-minute warning, an 8-minute warning, a 7-minute warning, and a 6, and so on. Eventually, I get about 40% in people in on that basis.
Thank you. You have 40%. Please go.
Okay.
You have a quorum.
All right, I have a quorum. I got into this business in the corrosion field, and Mike McCoubrey knows it very well because he was working with us at EPRI, and we found that small quantities of impurities were causing a difference in corrosion that was catastrophic in many cases. And in the process, I looked around in the science field, and I found, well, the people who make field effect transistors at General Electric found that if you had as much as 10 parts per million of sodium in that gate region, they couldn't reproduce the field effect transistors. So when they found that out, they could eventually become successful. A few tenths of a part per million of sulfur and phosphorus in the grain boundaries of stainless steel is catastrophic to stress corrosion cracking, a major cause of outages in nuclear power plants. And in case any of the geologists are here, a few thousand parts per million of magnesium makes the black smokers at the bottom of the sea, on those hot springs along the ridge lines between the plates. So a few ppb of things can make a big difference in the human body. We have to have iron so we don't get anemia, and there are even a few unprincipled people who make you afraid of all sorts of parts per millions of things in your diet. They've been told that a few parts per million of mercury in your from the teeth, you know, your amalgam in your teeth is causing you to lose your hair or whatever. And I've lost my hair, so it must be the reason. But so this business can be abused, to be sure, and it isn't always true that small quantities of things cause a big change. So, however, when I saw in the early experiments no neutrons and very few tritium atoms, I said, well, maybe it's the impurities in the palladium that are the difference and make this thing possible. First thing we came up with is boron 10, which was obviously already there at about 100 parts per million. And I pursued that for a while. And then more recently, I observed zinc and gold and iridium and silver and cobalt in these samples that, similar to Dr. Arata's, in fact, some of his samples actually, which were only exposed to gases. Remember, electrolysis can deposit on the cathode anything that's present, either in the anode by dissolution or already in the electrolyte. So it can deposit on the cathode and you'll see it there. However, in the gas contact systems, that method of getting your impurities isn't there. So you don't have that to worry about. So that's why I thought this was more significant than any of the things that we've done in the past, since we were in the past getting only cathodes from electrochemical cells. So this is a story that I want to show you on the first slide. We did the time of flight secondary ion mass spectrometry, which you can only observe the first few surface layers on a sample, but that's also, you can see almost all the elements. And it just turned out, I was looking at zinc at the time, but turned out that the lithium 6-7 ratio looked askew. And so I switched to thinking about what that meant. I had 17 samples from various people, 3 from Chinese work here, and 14 from other, mostly erratas, or attempts at errata style experiments, exposing the powdered high surface area palladium to high pressure hydrogen or deuterium. So, and they were exposed for about 1 to 6 months. And here's the first set of data that I took from 4 samples. The virgin sample on the left here is the ratio of lithium 7 to 6, which normally on the Earth is 12.48. You can see it's pretty close to normal. And these are the 3 active samples that produced excess heat in the errata experiments. And you can see that the 7 to 6 ratio ranges from about twice normal down to just maybe 10 or 20% above normal. But nonetheless, always above normal, implying a depletion in lithium 6 relative to lithium 7. Then SRI attempted and did some supporting replicas of the errata style of cathode and observed excess heat to the tune of 64 megajoules in the D2O case and -1 plus or minus 6 megajoules in the hydrogen or water case. And here are the 2 cases where we have, I had 2 sets of these. You can see that they're not very impressive, but it is still positive relative to the terrestrial value. 12.5 is the terrestrial value. So that the D2O is slightly higher than the H2 in this case. In this case, it's reversed, so it's a little ambiguous, but the limits of error are such rather high for this H2O case, a lot less lithium present. So the limits of error include this difference. And again, this is a set of powders from the errata sent to Kubi to measure the helium-3-4 ratio. And Mike, I don't have any data on these from the excess heat, but I assume that they were in an errata-style cathode and did produce something. And this is the set of ratios that I got there. I have just designated 8, 5, 2, and 1 and terrestrial lithium. And you can see that here's one that's a little below, but all the others have a slight increase over that of terrestrial lithium. So the hypothesis is still alive, but it's taking a few body blows. Here's the catalyst of palladium, similar to that which Lester Case had introduced. 0.5% palladium on coconut charcoal. And here we have SC1, which is here, the virgin material. And here's SC2, which had produced 11 parts per million of helium-4. And so you can see it's not impressive, but it is positive. And then we had the SC20, which gave no helium, versus SC19, which gave 9 parts per million helium. And we see a rather well above the limits of error increase in the active sample versus the one that didn't produce any helium. Finally, we had a set of wires that were exposed to ordinary hydrogen, and that were done here in Tsinghua University. And here we had just 3 samples that I've been able to do. These are not powders now. And they were run for about 6-month exposures to light hydrogen, 2 active and 1 virgin. And the virgin is here, sample B, which is very close to terrestrial lithium. D didn't seem to be very much of an active sample as far as I was concerned with lithium 7-6, but E was a factor of 2 increase or depletion in a 7-to-6 ratio. So I got this fairly early in the game, and was quite encouraged by that, assuming that it might turn out to be, really a barn burner. But as usual, it's not quite that. Now, there are a lot of questions you could ask, and I'm going to save some of these view graphs for those, but I guess I should show one particular one. One of the intriguing things is that there are quite a few reactions with lithium and hydrogen that are shown here, all of which give a large Q, and they produce helium-4. I didn't show the 4 up there, but it should be. And also, you get the DP reaction here, giving 5 MeV. We can make tritium also with lithium-6. These are all lithium-6 reactions. And notice we have 1, 2, 3, 4, 5 lithium-6 reactions and only 2 lithium-7 ones. And we're seeing depletion in 6 versus 7. Also, you can see the highest Q one is very similar to that of DD reaction, 24 MeV. So 22 MeV is a very substantial Q. Lithium-7 has a 15, and even protons give you 17 MeV with lithium-7. And I don't know why you wouldn't see some excess heat with protons, assuming that any of these reactions are possible. So I would not lose heart about looking for excess heat in samples that might be containing lithium. Now notice I've seen 17 samples, and I've seen lithium in every one of them at the few parts per million level, which says it's a very universally present contaminant, or a tramp element, or whatever. So it isn't that we haven't always tested lithium, because it's always been present in some form. It is easy to observe, easy to measure, and there aren't many ways that you can be fooled by lithium-6 and 7 in a time-of-flight SIMS, because there aren't that many ways to make mass 6 and 7 with multiple atom ions, which is the bane of the existence of people working at the 100 atomic mass unit level. So let's see. Well, I have about 21 papers here, and anybody wants the detailed paper, I think I'll stop now and ask some questions.
Thank you. Thank you very much. Questions? Yes, please. Go ahead.
What was the error of measurement of lithium content? What was the error?
The error? Well, in the paper it shows what the errors are, and I'll show you some of them. Here are some of the those are the ratios. I guess I go with the absolute. Okay. So here you have the entire list. They're in the paper, and you can see they're outside the limit. The 1 sigma range is shown here, the lowest to the highest, in plus or minus 1 sigma. So 12.5 being terrestrial. This palladium A is clearly outside that limit. Palladium B clearly outside the limit, way up there, 20.6 to 23 and 4. Here's one that's well above the limit. Here's one that's within almost the limit.
I see, thank you.
Does that answer your question?
Next question, Professor Takahashi.
The factor to increase the big number, interesting. But I have a question.
Sure.
We used to measure the nuclear cross-section for the lithium and deuterium reaction, and for the purpose of plasma and the particle interaction for hot fusion. And we know the reaction cross-section with lithium-6 and deuterium, we measure down to 100 kV.
100 kV?
Yeah. And we found the reaction cross-section is comparable for lithium-7 plus deuteron producing 2 alpha particle and neutron, and lithium-6 plus deuteron producing 2 alpha particle, just comparable. And in theoretical respect, I think the reduced mass for lithium-7 and deuteron reaction is a little bit larger than lithium-6 and deuteron reaction, about 10%. That makes a difference in barrier penetration at very low energy. However, the contact distance for making a strong interaction, making a real fusion or some nuclear interaction, the lithium-7 has a larger distance. So far, that compensates each other. And that makes a cross-section just equal, almost equal. So far, if you see you say the lithium-6 plus deuteron reaction producing helium-4 to helium-4 is a reason of excess heat, the amount would be 10 to the 12 per second per watt. So far, for megajoule, we should have 10 to the 18th product. Okay? So for natural lithium, we should have a neutron 10 times. So that's a reasonable amount of neutron we have never seen.
I agree, and the only explanation I can give is that the Qs that might be dominant in deciding which you get. And the neutron reaction is one of the lower Qs, about 1.67 MeV. Well, here's the Qs.
Yeah. Sorry, table 4. For the lithium-6 reaction, 22 points.
Lithium-6 for making a neutron, here's the only one making a neutron.
Yeah, I mean the
1.67 MeV.
Yeah. I mean the lithium-7 reaction producing neutron.
Oh yeah,
which
that's
has a
15
higher
MeV,
Q value.
right? That is a
That
higher.
cross-section is comparable to the lithium-6 plus D to 2 alpha
Yeah,
reaction.
if I believe,
Just comparable.
if I believed nothing but high energy physics, or normal nuclear
I
physics.
have a paper here, so give
Okay,
me later.
if I believed nothing but normal nuclear physics, I wouldn't be giving this paper.
Usually you need an explanation why you have such kind of selection,
Right.
activity.
Well, I thought that it's a miracle enough to get DD, but it doesn't take much more of a miracle to get D lithium.
Of course, you have to explain why you don't have a DD reaction.
How's that?
Of course. To use your DD reaction, you didn't see.
Well, I'm sorry, I don't understand. If you're trying to tell me, ask me another question.
Yeah, usually we should have a deuteron reaction also there.
Yeah. Well, the reason that I shrunk from that idea was that we weren't getting the normal, similar number of trillions and neutrons. And I thought, well, maybe some other reason is, some other thing is going on here, and that's the reason for the difference in trillion
But,
and neutrons.
we have no distinction between lithium-6 and lithium-7 for nuclear reaction with deuteron.
In the first order, you're right. Right.
Thank
Any
you.
other
Next
question?
Yes, please.
I know that you check to make sure the hydrogen reaction is not occurring as far as lithium hydride coming off by looking for and not finding Li8. But in the United States, the normal ratio of atomic weights for lithium is crazy because the Atomic Energy Commission, back when it existed, dumped so much lithium that had been separated out
Right.
into the commercial market.
Right.
Did you check before and after on these lithium ratios?
Well, I tried to get a virgin of the same material. That's where I showed the virgin material, assuming that the virgin isn't so likely to be different from the subsequent used ones. And otherwise, I was aware of the fact that if you take off the shelf lithium salts, you see a wide range in the ratio, probably due to the problem that you're mentioning. But that's why I chose to, wherever possible, to get a comparable sample that should have been similarly treated and should have the same basic impure lithium ratio, 7 to 6.
Further questions? If not, then I thank you very much,
Thank you.
especially for
Bye.
keeping the time. I appreciate it very much. Next paper is by Dr. McCuckering. So we follow now the normal schedule.
Starting off with the microphone, Tom. That's right, I found it. Well, thank Professor Lee very much for inviting me to this conference. Very beautiful site. What I'm going to talk about today is what I think is the principal problem that we face in this field, certainly the criticism that I get all of the time when discussing this field and this work. What about replication? And what we're trying to do, what I've endeavored to do with my colleagues at SRI, particularly Fred Tanzella, is to form some collaborations where we can really focus on the problem, the issue of replication. Having said that and raised your hopes, I must claim to have been almost totally have failed in this endeavor. But one of the primary collaborations that we've established is with a group at ENIA Frascati, particularly Vittorio Violante and Paolo Tripodi. There's a huge number of people that have contributed to this work over the years, and I list them here. Every time I show this list, I recognize that at least one person has been left off the list, and I'm usually looking at them in the audience. But purpose of this, or the details of this formal relationship that we've established with ENIA, the following 5 objectives. First, means to obtain, control, and sustain high loadings, high hydrogen to palladium and deuterium to palladium ratios, particularly in small dimension objects, wires, foils, and coatings. Something that Dr. Violante